Hey, welcome back to the Robotic camera arm build series. On a previous video, I built a side mount worm drive gearbox to power the shoulder joint after the bevel gear design failed. I posted the miniature right angle gearbox video before I tested it, so I was not aware that it would also fail. Hit the subscribe button and check out the Robotic camera arm build playlist. Also hit the like button so the algorithm knows to push my failures to more people. After the failure of the Mark II shoulder joint failure, I attempted to fix the problem with that gearbox by adding a torsion spring assist. So let's check out the build of this spring assist and I will share the progress of this build. To recap, this is the right angle gearbox. My attempt with this design change from the bevel gears was to change the ratio of the gears to a degree that the torsion forces that the arm was creating would be more shared across the gear train. If you remember from the bevel gear design, it worked very well for the most part. It was when I went to the 140% load test that it failed. The problem I had with that was not so much design failure as it was a procurement failure. I don't have the equipment to cut anything but straight gears, and buying off the shelf small metal gears is limited. So I had to make do with what I could get. This meant that I had to solve some other problems. One of the main problems was that the pinion gear was hardened and I was having trouble solving the issue of securing the gear to the motor. I did still learn a lot and it was still an interesting exercise of machining. In any case, I decided to go with the worm drive style design to increase torque. However, that one also failed. Stay tuned and I'll show you why that failed. It actually took me this long to figure out what I did wrong. Having gone this far, I came up with a simple design tweak instead of a full redesign. This is what is called a torsion spring assist. It consists of a coil spring mounted onto the opposing end of the shaft to take some weight off of the worm gears. It is simply an aluminum block with a coil spring inside that is preloaded to put twist on the shaft in an upward direction. Let's check out the machining of this part and I will discuss what I have been learning from this build. The aluminum block started out as a chunk of 3x3 by 1 inch thick 6061. Started off by shaving the size down to 3x2 by 1 inch thick. 3x3 is all I had on hand. After the block is shaved down to size and deburred, I set it back into the mill and zeroed the DRO. I love these edge finders. They are simple and plenty accurate, and I have only broken one my entire life. Here I'm making the cavity in the block to hold the spring. This cavity is 1.75 inch in diameter by 0.75 inch deep. I need to make a starting hole so I can finish the bore with my boring head. Since it is a blind bore, I can't use drill bits and I need the floor of the bore to be flat. This is so the spring doesn't have anything to catch on. I start with a 1/2 inch carbide end mill. Why solid carbide? Because my mommy said I can, and I have a bunch of these from a previous job. One thing I don't have on this mill is a Z-axis readout on the DRO, so I need to use the table to depth the hole to maintain accuracy. The scale on the quill is just a simple ruler, and I am too sphincterally retentive to eyeball this on a precision machine. So after locking the quill, I use the scale on the hand crank and drive the part into the end mill. This build has been discouraging for me. Discouraging in the sense that I usually don't have failures like this. A lot of work goes into each design and machining process, and it's depressing when all that work comes to naught. I need to open the hole out in steps, but I don't want to do it in one go so I don't break something. I move from the end mill to a counterbore cutter since the center is cut out. I need the hole as big as I can get it so I don't spend eternity here with the boring head. When using a counterbore without a center pilot, it's easy for the bit to walk when starting the cut. I started with a 3/4 counterbore and then a 1 inch counterbore, using the same method to control depth as with the end mill. The counterbores are high-speed steel for those of you that wheezed that I used a solid carbide for something so trivial. I really thought the first gear design was sufficient for what I was looking for. I wasn't looking for some sort of achievement award for this build, but I was looking for a certain level of reliability. The first failure wasn't too jarring, but it made me rethink my approach. This build is a little out of my comfort zone. I'm used to less constraints. There's not a lot of room in this build for over-engineering. And I don't want a robotic arm that looks like a howitzer holding a feather. It is not a problem you can just throw money at, as I mentioned previously. there is a limited availability for off-the-shelf items. Once I have the 1-inch hole set, it is time to switch to the boring head. This is an old boring head. I recently gave it a good cleaning and adjustment, and it has been flawless ever since. It is very accurate. For the depth on the boring head, I will use the power feed on the mill with the depth stop. The depth stop is just an adjustable hard stop for the quill that disengages the feed. It takes a little fine tuning for the first pass, but it is reliable for the next 20 cuts. I am taking 25 thou cuts at 3 thou per revolution. I have learned a lot with this build, not just for redesigning, but machining as well. I have had to come up with some unique methods for work holding, and it really has pushed my machining capabilities. I have learned that the machines in this shop are capable of some pretty fine precision, and that has been the reward so far. Of course I want this to work the first time, but sometimes success is not in that sprint to the finish, but that you keep going. The saying, "You haven't failed until you stop trying." Once the bore is done, it's time to start drilling the mounting holes. And through the magic of television and incompetent videography, boom! The holes are complete and the block is flipped over and a counterbore for the holes has been put in. Now for aesthetics, I'm going to put a chamfer around the 3 sides of the block. Here I'm using a 90-degree 6-flute countersink for this. I only buy high flute countersinks. I find that they have less chatter. I am also using this cutter in conventional milling. With the size of cut and my machine, I don't want to risk the cutter grabbing. I set a depth that I like since this is just for looks, and I noted the distance from centerline that I started at, so when I do the other 2 they will be consistent. Now we are on to the other modifications. I need to add holes in the shoulder joint bracket for the block that I just made. Clamp the bracket in the vise and using the test indicator, zero the mill on the bearing hole. A note on this test indicator: if you haven't gotten yourself one of these, then you are missing out. This thing was cheap. I bought this at MSC for $100. Now they're about $180. It was the cheapest test indicator that they had, and it is awesome. It saves so much time zeroing onto round holes. Edge finders take 10 times as long. These holes need to be tapped for the mounting bolts. They get a 1/4-20 tap and a little deburr at the end. This is something I always do wrong. You're supposed to deburr before you tap, but I always end up deburring after tapping. I did end up buying an Albrecht keyless chuck for this mill a little after this that saves so much time on switching out tools. Now I'm just taking care of some of the deburring since the shoulder joint bracket is broke down. I couldn't deburr these holes because I used the titanium rings as guides for drilling and tapping. I couldn't get to these holes until now. It is hard when you are designing something this compact and pushing it to its limit that you not only test your abilities but your resolve. I know it's easy in hindsight to say to yourself, "Why didn't he do this?" or "This was a stupid choice." Trust me, I know. A lot of planning was done in the design phase for not just what I wanted the arm to look like and do, but also what I had available, both machine-wise and parts. It comes down to picking a path and going with it. I clearly didn't take the easy path, but I was trying not to take the hard path. I sort of wanted my own path. The next piece to make is the shaft. The shaft for the bevel gears was flush on both ends, and the shaft for the right angle gearbox was flush on the end where I need to mount the spring block. So I need a new shaft where I can attach the spring. I decided to do this out of brass like I did for the right angle gearbox. This is actually 932 bearing bronze in 1-inch diameter. It was some that I had. Brass should be sufficient, or so I thought. Stay tuned for why. The first step is to turn it down to the starting diameter of 3/4 inch. That is the flange diameter that I need to bolt the worm gear to the shaft. I'm going to do something weird here. I have mentioned before that I don't have a huge selection of toolings. Also, my smaller lathe is kaput. I am going to use what is called a dead center to support this. A dead center is a lathe support that doesn't turn with the part. Like a lathe center, but dead. This is because my live center is too big for me to get the diameter I need with my tooling. However, I do come up with a solution for this. Dead centers are a last choice scenario, and I realized this quickly. The dead center keeps digging into the brass. As a solution, I realized that I can use my parting tool like a turning tool. It's only brass, and I can take sufficiently small enough cuts not to break anything. So after marking the flange location with Dicom and getting sick of constantly adjusting the dead center as it grinds into the brass, I switched to the live center and the parting tool. This works great because I can get the parting tool closer to the chunky live center. The flange has a taper on the inside surface for strength because why not? The lathe tool I have here is a high-speed steel form tool to cut snap rings. These snap rings will sit up against the bearings to hold the shaft in place and hold the bearings in. Now we are back over to the mill to put holes in the shaft flange for the gear. This gets 4 holes. I like to spot drill and then tap before moving to the table. I think that changing the table is more work than changing a tool. Now I need keyways on the shaft to lock the shaft to the knuckle joint. The knuckle joint is the mating part of the shoulder joint attached to the first arm. These need to be fairly accurate, so I have enough keyway for the joint, but not too much that it encroaches on the bearing. These are 0.125 inch wide by 0.125 inch deep keyways. I'm also going to put the slot in the end of the shaft that the spring will register onto to hold the shaft. I'm getting as deep as I can, but not too deep that I weaken the end. About halfway through is good. Using the rotary table and my mini pallet, I rounded off the end of the block to suit the bracket. This is actually fairly simple. Once I zero the mill to the bracket and mount the block onto the bracket, I can then use an end mill to shape the end to match the joint. I will also use the chamfer tool to put the chamfer back on because that just looks better, more aerodynamic. The last step before assembly is I need a notch in the block to hold the outer end of the spring. The spring works by storing energy when it's wound. Do you notice the band that is around the spring? This is a grenade pin. A grenade with no timer. This spring is not wound up to its full potential, but just the initial factory wind is enough to cause serious damage if that band comes off when the spring is not contained in the holder. I luckily have some experience with this, and I am very aware of the potential danger, but that band is only held on with friction. I just make the notch over in the bandsaw and then clean it up with a file to fine-tune the fit. Okay, we're at final assembly. I have put this thing together so many times, I think I might have had my eyes closed just to feel something at this point. The gearbox gets attached. And then I realized that I forgot the bearing under the gearbox. So I opened my eyes and detached the gearbox to put it back together the right way. Then the shaft with the gear attached. The first snap ring is already mounted. I was very precise with this location because the snap ring sets the depth for the gear to make sure that it is meshed correctly with the worm gear. In a worm gear assembly, the driving gear is called a worm and the larger driven gear is called a gear. Keyways for the knuckle have to get slid in from the center for each fork of that knuckle. I couldn't do a full-length keyway because I wouldn't be able to slide it through the bearings and forks of the knuckle. Either way it worked. The last snap ring is installed and now the shaft is locked into place. Now for the fun part. I need to install the torsion spring into the bore. The band that holds the spring is meant to slide off when it's pushed into the bore. It was a tight fit, which was good. The spring will shrink as it is wound tight. Putting on the torsion spring is where my brain started working overtime. I was trying to imagine the direction that it needed to be wound to counter the torque of the arm. Here I am counting the turns. The spring is rated by rotation. This way I know I am getting maximum strength on the spring without overwinding. If I overwind the spring, it won't really give me any more force, but just weaken the spring and potentially break it. The block is bolted down and we're ready to test. I hinted at the major flaw in this design. I discovered it while editing this video. It may not sound like much, but to me, to recognize that is a small success. It means that I could modify this design and make it work. This actually should have worked, and the reason it didn't is simple. Let me know in the comments if you know why it didn't work, besides the obvious of the guy on the screen. I'm going to give you a glimpse into the gearbox mechanism and let me know if you notice what I missed. I didn't miss this in the bevel gear design. I will give you a hint, it's not the missing screw. Let's watch the failed test and see if you can catch it. I do a quick motion test first. There is a noticeable lightness in the arm, so the spring is providing some upward force as designed. If anything, it helps with dampening. This is where I noticed the possible problem, but continue anyway. What I expected to happen was the gears to be stripped when it popped. If you guessed that I didn't have any support on the shaft on the gear end, you would be right. Right here, I have an overhung shaft with a lot of force on it. The bevel gear design had the same force, but I added a second gear to counteract the force that wants to push the gears apart. I should have put an outboard bearing on the end of the shaft in the box to hold that shaft. The gears weren't shearing, the shaft was bending. This is why after the failed test the arm is loose. I was puzzled here because I couldn't see any sheared gears. Most of the time it's a keyway or a sheared fastener. I'm going to now check those brass shafts to see if there's any run out. I put an outboard bearing on the worm gear shaft. This was stupid of me not to put one on the main shaft. These are the things that you learn doing this type of design and build. Sometimes the design is wrong, sometimes was miscalculated, or something was made wrong. Sometimes it is oversight. It was probably some hubris on my part, and maybe I'm a little worn down from this project. But seeing the video of the build is letting me reevaluate the design in a way I couldn't see before.
Spiral. Awesome. Like that's like. Oh yes. Come on in, Patrick. So.